Good afternoon. How's everybody doing? Pretty impressive conference, I got to say. This is my, I guess, third one. Well, the real one was last year, and there was a meetup before that, and went from, I guess, 40 to, what was it last year? 300 to, what is this? 1,200? 1,000? A lot of fun. Right, I'm Quinton. It's my colleague Madhu over here. We're going to be talking to you this afternoon about Cluster Federation. You've probably heard the term mentioned in numerous talks today. Hopefully not too many of you went to Brandon's excellent presentation this morning, or demonstration. There's going to be a little bit of overlap between what Brandon spoke about and what I am going to be speaking about, in particular Madhu's demo. But with no further ado, let's get going. So we're both at Google at the moment. We're active contributors to the Cluster Federation project. As I'll discuss later, there are many, many other contributors. I don't want to have us take more credit than is due. This is very much a community effort. And I guess Cluster Federation is one aspect of what we're going to be talking about. The other part of it is building global, highly available, multi-cloud services. And this is a huge mouthful, but I guess it's important. Multi-cloud, so the stuff runs across different cloud providers. You can run clusters in different public clouds, on-premise, etc. It's highly available. You can handle outages of clusters, and it's global. You can do things like low latency serving of your customers around the world. So this is roughly what we're going to be talking about: history, motivations, some of the challenges associated with Federation, some examples. Madhu's going to do some demos of the existing software that we have and how it works. And then we're going to talk a little bit about the roadmap, where we came from, where we're going to, etc. So this stuff I think most of you know already. Google has very large data centers, so do many other people these days. Amazon's data centers don't look too different than this either. But this is kind of stuff that you all know. This is why Kubernetes exists. This is why Borg, which came before it, exists, because managing this stuff with anything other than pretty sophisticated automation becomes a nightmare. What not everybody necessarily thinks about at first pass is that there are also lots of these data centers around. And there are many. These are Google's data centers as of several years ago. That map looks different now than it does on the screen. For the Googlers in the audience, this comes from our public website. This is not internal information. But Google's not the only company that does this sort of scale anymore. Amazon's, I think AWS has got 35 odd availability zones. You only have to think about the, telcos of the world, how many airports are there in the world. A lot of these problems start looking like multi-cluster problems to solve. So we started thinking, what if we took the Kubernetes machine automation model, which most of you will be intimately familiar with by now, and applied this to entire data centers? So Kubernetes, if you zoom out to 30,000 feet, looks roughly like that. There's a whole lot of detail inside that pink box in particular, but if you zoom out far enough, you've got a bunch of users interacting with some control system via APIs, user interfaces, command line interfaces, etc. And ultimately what they do is they put containers onto machines, servers. And this, for the most part works very well. And all of these fancy abstractions that we've created, replica sets and services and ingresses and all sorts of other things, basically allow you to, do this stuff in a sane fashion, tie all these things together. So what if we took that principle and we replaced the things on the right-hand side with entire data centers? And what if they each ran in different cloud environments? The classic three would be on Google, on Amazon, and on your on-premise data centers. The model looks very similar. The APIs that are used to the clusters are just the good old Kubernetes API. The API on the far left-hand side of that diagram is also actually the Kubernetes API. So all of the concepts that you've learned, all of the tooling that you've built, etc., speaks the same language to the pink box on the left-hand side as this pink box on the left-hand side. Makes sense so far? So why is this interesting? I mean, besides being an interesting academic exercise, why is it valuable to people using Kubernetes? There are a whole slew of reasons. I don't want to spend the whole afternoon on them, but I'll just whip through a couple quickly. High availability is obviously one of them. Clusters can fail. You upgrade clusters, you upgrade your software in them. They have, acts of God befall upon them. I'm sure more than one of you have experienced AWS zone outages, for example. Low latency to your users is another classic example. If you have a global service, you want to serve your stuff typically close to your users. A pretty standard distribution pattern is having a few data centers on each continent so that all European users are served out of Europe, all Asian users are served out of Asia, and all North American users are served out of North America. And sometimes for more sensitive applications, you can subdivide that more. So, Google search typically would not serve an East Coast US user out of the West Coast because the latency would be noticeably worse. Policy enforcement and auditing. If I go back to this diagram, there are often, company policies that determine can this group run their applications on AWS or GCE? Which clusters do they need to go into? Do they have to be in PCI compliant data centers? Is this sensitive data? Do we need to, take cognizance of that? And so this kind of thing is much easier to enforce if you have some kind of a central control plane that makes these decisions. Provider lock-in avoidance, and this is pretty obvious. If you want to move your applications around between different cloud providers, it's much easier if you have an orchestration layer to help you do that. Scalability, a lot of users are, asking questions around what if I have more than 2, 3, 5,000 nodes that I need to orchestrate my containers across? Can I build a 100,000 node cluster? And the answer is it's not such a good idea. Even if everything worked fine, it's just generally not a good idea. It's not something we do in Google very commonly. It's much better to build a whole bunch of multi-thousand machine clusters. One, they fail independently of each other, so you don't lose 100,000 machines at once. And there are various other reasons. You typically don't need 100,000 machines near one geography. You typically need to serve more than one geography if you have that number of machines. Capacity overflow, and there are many, many other examples of why this is useful in practice. So there are two primary building blocks. When you start thinking about this a little bit further, there are two primary building blocks that are necessary in order to make it useful. The first one is network traffic management, so being able to distribute traffic both from the outside, from the internet, to the correct clusters, and also from a cluster to another cluster. And so that's something we're going to be talking a little bit about. How do we do service discovery from the outside? How do we do service discovery from the inside of a cluster? How do we do external load balancing, geolocality, so ensuring that the lowest latency access to clusters from users? How do we do failover if clusters go down? How does traffic get redirected to the other clusters? And the other component of the problem we're solving is resource placement. So where do we put all of the load balancers? Where do we put all of the worker pods, et cetera, that sit behind these things? How do we allocate IP addresses? All those kinds of things become important, and you need to figure out how to do that sensibly. Otherwise, the idea is not very useful in practice. All right, so this all sounds great. Where are the challenges? And I didn't want to make this sound like this was all roses, and most of you will probably be familiar with some of these problems. There are different bandwidth charges between different data centers. I've tried to illustrate that in the diagram. If you're going between inside a single zone and a single cloud provider, typically your network bandwidth is free and your latency is effectively 0. As soon as you start going between different regions, between different cloud providers, that can change by many orders of magnitude. There are different service discovery techniques depending on which cloud you're running on. You might have DNS names, you might have IP addresses, you might have some other service discovery mechanism. If the promise of Kubernetes portability is to be kept intact, we need to make sure that the mechanism that a given application uses to find the other parts of it should ideally be consistent across all of these deployment methodologies. And obviously, when you have large numbers of clusters, your monitoring challenges become more complex as you go. So those are things that we also need to figure out. And I'm not going to dwell on this too much. There's a lot of words on the slide, but basically, it is worth recognizing that there are different classes of applications. There are the very, very loosely coupled applications where the pods don't talk to each other a lot, or subsets of them do, but not the rest. And they can pretty much be deployed in any data center and can serve independently of each other. There are There is the other end of that spectrum where you have very strictly, tightly coupled applications. I was speaking to someone earlier over lunch about video rendering, where the latency and the bandwidth in particular between storage and nodes and each other, et cetera, is very critical. And obviously, if you separate those nodes by across regions and across continents, that doesn't work as well. So there are some applications that are more easily federated than others, but it turns out that the class of applications that do federate well is substantially large and interesting enough in its own right. Past, present, and future. So what have we done? What have we built? This is all very hand-wavy requirement stuff up to now, but what is actually there? So we started development of this in Q2 of this year. It's important to note, as I mentioned earlier, the API is 100% Kubernetes compatible. So no relearning or retooling or anything else. The same concepts that you come across in Kubernetes you'll see here, and the semantics are very, very similar. And you can take your existing applications and deploy them with their current configurations directly into Federation. And with some approximations and with all the caveats that I mentioned on the previous slides, for the most part, things should work as you intend, and you can tune from that point. Q2 2016, we built the basic control plane, all of the test infrastructure and everything else that's required to make this stuff real. We also built federated services, which we'll be demonstrating in a few minutes to keep you all excited. Slides with no demos is boring. Federated services provide you with multi-cloud, multi-region intelligent service discovery. So what that means is you can have your service spread across AWS, GCE, on-premise if you like. You can use the same service discovery. You can look up the same DNS name wherever you are. You will find the closest shard of that service. If you have one in your cluster, you will find that one. If there's one in the cluster next door in the same region, you'll find that one. If it's nothing available there, you will go further afield. This is all dynamic, so as pods disappear, fail health checks, etc., all of the DNS infrastructure to make this work is automatically updated by the Federation control system, so you can sleep happily while all of your traffic gets redirected around the planet. Q3, we focused on, we sort of moved from a build the basic control infrastructure mode to let's solve some really interesting problems. We released federated ingress for GCE, so you have a global L7 load balancer that does some pretty sophisticated load balancing across the globe based on a single IP, so there's no DNS dependencies, there's no TTLs and DNS caching problems associated with that. We also did replica sets, so you can deploy a replica set that spans multiple clusters. We do dynamic allocation of replicas. If clusters become unavailable, we reschedule the replicas into other clusters. If you add clusters to your federation, you can optionally redistribute the replicas that you have across the new clusters. Secret propagation, so a pretty common use case is needing to use secrets to distribute credentials, etc., and you want to keep these consistent. As soon as you have a large number of clusters, you have significant configuration problems. This makes it a lot simpler, and events just make it easier to see what's going on inside your federation. Q4, we realized, and we'll talk a little bit more about this later, that creating a federation is actually non-trivial. As much as we tried to make it as trivial as possible. So we spent a lot of effort in Q4 making that a lot simpler to do. We built some tools that will allow you to deploy a federated control plane or federation control plane easily and federate clusters into that with single line commands. We also built federated deployments. So those of you who know Kubernetes deployments, they give you things like server-side rolling upgrades, etc. These are implemented in Federation as well, so you can do rolling upgrades across multiple clusters. Daemon sets, these are things that run on all the nodes. If you want to run on all nodes in all clusters, you can do that with a single daemon set at the moment. Jobs, config maps, etc. So that's a little bit about where we came from, where we're going at the moment, and in the future, without wanting to, whoa, some feedback happening here. We plan to spend some effort on the following areas in the coming year. Policy-based resource placement. So something that is quite commonly needed is the ability to have a distinction between what an application wants. So an application might need certain kinds of nodes or certain connectivity to other parts of the application, but a company or some sort of other party other than the application deployer might have another set of policies, which is we preferentially run our stuff on premise, and when we run out of capacity, we run it in a cloud, for example. So we like to overlay that policy on top of whatever the application specified policy is, and that should ideally be something that's easy to declare, easy to understand. These are the people specifying these policies are not always engineers and highly technical people, so these should be easy to express and easy to understand. Improved identity and access management. You can imagine when you have all of these different cloud providers, each of which might have different concepts of identity, and you've got this control plane acting on behalf of potentially multiple users against different clusters and different cloud providers, things can get complicated pretty quickly. We've got a very simple model at the moment, essentially to prove out the concept, but there's a lot more work to be done there to make sure that it is solid. Stateful apps and federated persistent storage. Doesn't take too much insight to realize that data doesn't magically replicate between data centers or cloud providers. So in the same way that Kubernetes pet sets, or I guess they're called stateful sets now, there was a fair amount of effort put into making sure that we knew how to handle stateful applications well. That problem is still there for federation. There's work to be done there. We have some pretty good ideas of possible avenues of tackling the problem, but nothing's been built yet. Hybrid federated ingress, as I mentioned earlier, the ingress that we built in version 1.4 is based on Google's pretty fancy L7 load balancing infrastructure, and not everybody has access to that, but we would like the abstraction of federated ingress to work irrespective of whether you're running cross-cloud on Google or not. So that's, again, we have a design, we have some interim, at least some initial implementations, and we hope to roll that out next year. Private federated services, again, more details if you need them available. How do you get hold of us? As I mentioned earlier, this is very much not a Google-only effort. This has been an effort by many, many different companies. I just called out the main contributors on the right-hand side, but there were several others. My apologies if anyone's been excluded. Huawei, CoreOS, Red Hat, ourselves at Google, and eBay have been just some of the major contributors. We have a special interest group. The contact details are up there. Some of you have joined it. There's a very long list of people who are members of it, send emails, read what's going on. We have a working group that meets every Thursday around midday Pacific time. You can join that. You can see the working group notes. A lot of people have come to me since we've been here and say, oh, we know exactly what you're doing because we read the notes every couple of weeks and we know what's going on, even though I've never met them before. And finally, if all of the above fails, Quinton, Madhu, there are email addresses. You can get us on GitHub. You can get us on email. And now, with no further ado, I shall hand over to Madhu, my colleague, who will give you a demo.
Thanks, Quinton. Let's look at a demo of how Cluster Federation works. For people who went to Brandon's talk earlier this morning, there is some overlap in this demo. Brandon also showed you the money shot already. We'll go a little deeper here. So what's the problem that we are trying to solve today? I want to build a global service, and my service is a web service. In order to simplify the problem for this demo, I basically just have an Nginx container running in my cluster or a set of clusters, and I'll show you how I can run this service globally across multiple clusters which is connected to Federation or registered with Federation. So as a preparation for this demo, I have already created 9 GKE clusters. There are 9 of these, but in this resolution, it's really hard to infer. But basically, there are 9 clusters running in 3 GCP regions and in 3 zones in each of these regions. They're all running 145. And I have also set up or deployed the federation control plane on one of these clusters. We'll talk about the federation control plane deployment a little later in this talk, but let's assume that, or I have already set up the control plane, and I have also registered these clusters with federation. Federation is only responsible for managing the clusters that's already registered with it. So you have to explicitly register or deregister clusters from or to, to federation or with federation, or deregister clusters out of it. So in order to show that, I'll run this command. You'll use the same kube control command to see the list of clusters that are registered with federation. Also, there is one other point that I want to emphasize here. Kube control can talk to multiple clusters or multiple endpoints. Basically, it's specified through the kube control context. My current context is a federation endpoint. Once you have your kube control talking to your federation endpoint, all your commands look very similar. I just did a get clusters the way I would do get pods or get deployments. Just to show that, I'll show you what my current context is. So this is my current context. It's a federation cluster. So I have the entire setup now. What I want to do in my service is I want to display the basic Nginx homepage. But in addition to that, I want to show the region or the zone in which that particular page is running or that particular instance is running. In order to do that, I have a shell script here, bottom left. It basically contacts the GCP metadata server to fetch the current zone and writes the zone as an HTML to the local index.html page in that cluster. It just does that. This is a basic shell script. And I want to put this shell script onto the clusters. How do I get this shell script onto the clusters? There are many ways to do it. One mechanism to use is a config map. You can put this script into a config map and mount it on a file system in your cluster. At the time of this demo, we don't have federated config maps right now. We will have federated config maps in the next release, which is in about a month, but we don't have it right now, but we do have federated secrets. You can do pretty much the same thing with secrets. So what I'm going to do is I'm going to put this script into federation, which replicates to all the underlying clusters, to all the 9 clusters. So left bottom is my script. The command that I'm going to run, I'm going to clear this. So what I'm going to do is I'll copy paste this command. It's hard to remember these commands during a demo. So I just created a federated secret. If we want to verify, we can see that this secret is in federation now. We can do a YAML to see the details. The content is under zonefetch.sh key, which will be mounted as a script. The actual script itself is base64 encoded, but it's there. We can verify it if we want, but it's not really necessary right now. So just to show you, demonstrate, I'll also use a specific context, which is one of the underlying clusters in the federation. So this is the cluster, and we have the zone fetch secret even there. So it's already copied to all the underlying clusters, all the 9 clusters. So now we have the script. We want to run the script. How do we run this? I'm going to run this in a busybox container in all the clusters. But we don't want to just do that. We also want to display the page written out by the script as an Nginx HTML page. So I have a replica set, which is basically a federated replica set. But it is exactly similar or API compatible with the Kubernetes API replica set itself. So if you look at the replica set spec, it has API version, kind, everything the same. We have the metadata, name, labels, everything. And I say 9 replicas because I want to have 1 replica in each underlying clusters, 9 cluster. So I do this, and I have 2 containers in my replica set spec. One is a basic Nginx container, which reads from or which has the www page. And there is a second container, which is just a busybox container, and it runs the zonefetch.sh script. And we mount this script, which is available as secret in each underlying cluster. So let's submit this to the cluster, or let's submit this to federation and see what happens. Before doing that, I want to take a step back and set a watch command to show how the DNS entries work. Quinton already talked about DNS entries. One of the coolest thing about Federation is we just don't expose the service internally in the clusters. We also set up DNS entries for external clients, for clients which are outside the clusters. So we have two DNS provider implementations today. One is Google Cloud DNS implementation, and the other one is Route 53 implementation. We also have core DNS implementation coming up in the next release, but I'll use Google Cloud DNS. So I have one of these zones created in my Cloud DNS, Google Cloud DNS. I'll just set a watch on it. So you can see there are only two records, the namespace record and the SOA record. No A records or CNAME records. As I create my backend and my service, you'll see this getting populated. So let me go ahead and create the replica set first. I'm submitting this replica set to the Federation endpoint. So the replica set is created in Federation. It's created, the message says, so no need to verify in Federation. But in the meantime, I also want to create a federated service. Look at the bottom left. Is this thing visible to all of you in the back? Okay. So federated service spec looks, again, very similar to or exactly identical to the service spec in Kubernetes. So I'm creating an Nginx service, and there is a selector, ports, and whatnot, and it's of type load balancer. I'm going to submit this service to the Federation endpoint. All I need to do is create the federated service. Let's go to one of the underlying clusters, any arbitrary cluster, and verify that these things are actually created in the underlying clusters. I'm going to first go and look at, you can already see that the top right is getting populated with the records, CNAME records. In the meantime, I'll also show you whether the replica set is created in one of the underlying clusters. So we asked for 9 replicas. And we are looking at one of the clusters here, which is running in Europe West 1D. It has one desired replica. Its current number of available replicas is 1, and it is ready. We can also look at the service if we want in the same cluster. And we have the Nginx service running there. And you can see that the records are getting populated. So Brandon already showed you the browser side of things. It's easy to just use one of these DNS records that's getting created here on the right side and go to a browser and try it. But because of DNS caches and things, it takes a while for these things to propagate. So I'm not going to do it right now, but we could take a look at the end maybe if we have enough time. But what I'm going to show you is the intra-cluster traffic or the inter-cluster traffic or the internal clients. If you have a service or if you have a microservice architecture, it's not sufficient that your service is working from outside the clusters. You also want your services to work from inside the clusters. So if you have your service running in cluster A, you can access your service from cluster B because of federation. What's that? So I'm going to exit into one of the underlying clusters. I arbitrarily, again, chose Europe West 1D. It doesn't matter which one. It was just easy to copy paste here. So I'm just starting a BusyBox container and exiting and starting a shell. So like the Kubernetes services, federated service also gives you internal kubedns service discovery name, basically a DNS name. And the DNS name is very similar. If you look at the, well, this is not really visible for people in the back, I guess, so I copy paste it to one of the shells here. So top left, if you look at it, I'm going to copy paste this command, which is basically a wget. But I'm wgetting to or curling to one of these endpoints, which is a service discovery domain name within the clusters. So my service name is Nginx. I'm in a default namespace. The next part is, or the next infix is the name of the federation. We have a concept where you can have a single cluster can be part of multiple federations. So you can specify the federation name, and if you do this, you can get the local shard of the service running. If now I do have a local shard of the service or local backend in every cluster, so I'm getting the local version. If I did not have a local shard or a local backend, I would automatically be rerouted to one of the closest clusters. This is the power of federation, guys. Thank you. I'll hand back to Quinton, who will talk a little bit more about these things, and then I'll come back to talk about the federation control plane deployment.
Thanks, Madhu. Hopefully that was informative. What else do we want to talk about? So some of the stuff that you saw up there might have been a little confusing, lots of consoles, etc. So I just wanted to go through, what was happening behind the hood there. So what you looked at previously was a service. We can also do the same thing with an L7 load balancer, ingress load balancer. So essentially what happens is you make a call to the Federation API master. You specify where you want your application to run. By default, you can leave that out, and it'll just spread it across all the clusters, as you saw in the previous demo. But you can also specify which clusters you want it to run in and what the weights should be for each cluster. A single call that gets deployed across all the clusters. In this example, we only have 3, but a more common example is 10 or 15 or 20. You create the service. Similarly, that was created in all the clusters. This automatically, in the case of a global ingress, wires up an external global load balancer, which spreads load across all of the pods in your service, across all of the clusters. And upgrades can be done pretty painlessly. You can make a single command upgrade to upgrade your service across multiple data centers. L3, so same concept. This is, again, essentially a repeat of what Madhu just gave you in the demo, but perhaps a little more graphically for those who might not have followed. The specifications at the top right there are exactly the same as the specifications that you would use for Kubernetes. The control plane makes sure that all of these entities are created across all clusters, and all the DNS management is managed automatically for you. It's failure aware. It does health checks against all of the pods in your service and automatically removes and adds DNS records for you based on which pods are successfully serving at the time, and which data centers in particular. And this is just an example. If things go wrong, a certain cluster goes down, fails, automatically all the DNS stuff gets updated, the health checks fail, and your users get directed to a different cluster. Yes?
So, for anything going wrong in the normal situation, I'm interested in the case of the cross cluster.
Yeah.
So I have an app that needs to communicate with peers. So I have an app that's running in 4 open clusters.
Mm-hmm.
A pod in one peer looks up, say the DNS name for this app in another cluster.
Mm-hmm.
It gets back what and how does the network connection?
It's a good question. The answer is it looks up the same thing. So it looks up a name, which is the name of the service that it wants, and the name of the federation. So you can either specify, I only want to find that service if it's in my cluster, or the lookup should fail. Or you can say, I would like to find it in my cluster if it exists, or otherwise give me the closest replica of it.
In the case where I want to find a different cluster. So I done a lookup. I got an IP address for the service in the other cluster.
Yes, correct. For the load balancer that exposes that service externally, yes.
Exposes that externally.
Yes, so the current incarnation of this provides public services. So the services are exposed on load balanced external IPs and publicly visible DNS names. As you might have mentioned, might have noticed on the earlier slides, creating private services is definitely a user requirement, and we'll work on that in the coming future. So where the DNS names are internal to the clusters and the IP addresses are not visible on the public internet. Does that answer your question? Excellent. So as Madhu mentioned earlier, we're going to talk a little bit about how to create federation control planes. In fact, maybe Madhu, you want to take over. Madhu knows far more about this than I do. And just so you know, we got like
we already got applause from the other room. Maybe that's a signal. Right. So there's a hint right here. Federation control plane is another application in Kubernetes. So we started working with this assumption that we already have Kubernetes clusters. Why not leverage all the features that's available? So it runs as an application in one of the underlying clusters. Let's take a look at how that actually works, or the architecture. So if you want to create a federation, you want multiple clusters. That's exactly why you're creating federation. It's not really necessary that you create all your clusters upfront. You can create the clusters or provision the clusters at any time that you want, decommission them, join with federation, unjoin, and whatever and whatnot, every possible permutation and combination. But you need at least a single cluster to set up federation control plane itself, which we call as the host cluster. It doesn't matter which cluster is your host cluster. In my example here, I'll choose cluster 2 as my host cluster, and I have 3 other clusters already set up for me, but you can add clusters as you want. So a federation, for people who are familiar with the Kubernetes control plane itself, it looks exactly identical or almost identical. We have an API server, federation API server, like the Kubernetes API server. And that server's endpoint has to be exposed to the outside world for people to make API requests. So we deploy the API server itself in a pod, but we use the Kubernetes deployment resource or the API object. So the Federation API server is a deployment, and we expose that using the Kubernetes API service resource. And we have a Federation controller manager, and that again is deployed as another Kubernetes deployment. We need a data store to store the state of the API server like Kubernetes. So we have etcd, which backs the Federation API server state itself or the storage itself. And then we need to set up all the credentials, certificates, and all those things, and configure DNS providers, cloud providers, and whatnot. All these things can be done manually, and in my setup, I'm using cluster 2 as an example, but again, I want to re-emphasize it doesn't matter. Also, you can spread your control plane across multiple clusters. The current scripts actually don't do it, but we have a plan on making the federation control plane itself HA in one of the future releases. Not the one coming up in December, but in a future release. But you can do all these things by hand, but the problem is these things are a little error prone, but let's talk about that in the next slide. So once you have the control planes set up, you want to register or deregister clusters. In order to register a cluster, you basically send this API request, this object to the Federation API server endpoint. This is probably the only special API resource that we have in Federation today, the API to register or deregister clusters. So you specify the cluster name and the API server endpoint of that Kubernetes cluster and a reference to a secret which contains the credentials to access that cluster. And you submit this to your Federation API server endpoint, and boom, your cluster is registered. And you can start sending API requests to that. Again, all these things can be done manually, and many people actually do this manually. If you go look at Kelsey's tutorial, he has all the steps listed to do these things manually, but it is very error prone. So in order to simplify these things, we are building a new command line tool called as kubefed. It stands for Kubernetes Federate. It reduces both the control plane deployment itself and cluster registration and deregistration to 2 commands. Kubefed init will deploy the federation control plane for you in a single command, and kubefed join will register your cluster with federation again in another single command. There is an equivalent kubefed unjoin, but it's not listed here. Anyway, this is how the control plane works, and that's it.
Is that
Yeah.
the end of our talk?
Yeah.
Right. We have a few short moments. Anyone has questions? Fire away.
What's the security concerns now that you're dealing with this federation? Are there issues coming up with regards to security across multiple?
Yeah, absolutely. So the security story here is pretty weak at the moment. We explicitly decided to do that just to prove out the concept and get people to use this stuff in a sort of proof of concept context. The model is fairly simple at the moment. A user provides the credentials that they would use to access a cluster to the federation, and the federation acts on their behalf using those exact credentials. It's not secure, it's not multi-tenant, it's not the right way to do things, but it does enable you to at least play around with this stuff. The model going forward is going to be much more sophisticated than that. Essentially, the federation will impersonate particular, more than one different user and use their each of those credentials, which it'll get from an external source, to operate on behalf of the user explicitly, as opposed to pretend they are that person. Yeah. Yes.
Do you have a plan for how you're going to build, if you're going to build network policy across regions?
I don't know. I have not given much thought. What precisely do you mean by network policy in this context?
The network Ingress filtering.
Ingress filtering. I have not applied my mind to that problem, I must confess. The general principle is that what we do is we work through the Kubernetes API, and we've been adopting, the most important things first. But yes, anything that Kubernetes supports that you could reasonably expect to be implemented in the Federation control plane would be, on the roadmap. Exactly how we do that is not clear to me yet. Yeah. Yes.
Could you say a little bit more about how you intend to do high availability control plane? Like, will there be SCG clusters that span?
Sure. That's a good question. So the model is similar to Kubernetes. So at the low end of the spectrum, you have a single API server, you have a single controller manager, and a single etcd server, and these things get automatically restarted. So they're self-healing, but not highly available in the sense that if any one of them fails, you will have an outage for the period of time that it takes to bring up a new pod. The etcd server is typically backed by a persistent disk which outlives particular nodes, so it comes back again, reattaches the same disk, and life is good within a few seconds. The next step up from that is to have multiple API servers. You can have as many as you like behind a service. You can send your request through any one of them. Those are all backed by a potentially or typically a quorum of etcd hosts, so you have commonly 3 or 5 of these things. And in the case of 3, you can lose one and have it replaced, and you have no outage. You have a master elected controller manager, which does things like scheduling, etc. So you can't have multiple of those, but you can have a leader election, so you can have multiple running at the same time. And as soon as one dies, the other one takes over as leader. And then the extension that applies in the federation case is you can spread these things across multiple clusters. So a common HA deployment scenario would be multiple clusters in the same region, in the same cloud provider, so low latency, relatively low latency network connectivity, low cost, but 3 replicas in different availability zones. You can lose an entire availability zone and you will have no outage of your control plane. And the same goes for the API servers, multiple in different zones, and a controller manager which does leader election across zones.
When you have, sorry, that's someone.
I think there was someone back there. No? Okay, yes, it's you.
So when you have the federation spread across 3 clusters,
Yeah.
and then you lose the one you're talking to, how do you figure out what the next one is? Your IP fading over, or?
You could go one level meta. Basically, you talk to the API Federation API server itself exposed as a federated service, and then you're talking to that endpoint. So if one of your underlying API server fails, you're automatically rerouted to the other one. Does it make sense?
Assuming I know ahead of time where they are.
Well, if you set up a federated service, you have your DNS entry configured to talk to all the services. You just talk to the one that's closest to you, and if that goes down, your DNS traffic is automatically, like when you do a DNS query, you automatically get back a different A record, and you start talking to that.
And one thing that's worth bringing up here, a lot of people get worried about the resiliency of the control plane. It's important to note that the failure of the federation control plane does not result in the failure of all the clusters. It's completely independent. The clusters carry on running. Whoopsie. The clusters carry on running. Some of the DNS updates will not happen while the federation control plane is down, but everything else works fine. The load balancers that load balance onto all of those things are configured. Everything works. The replica set controllers in the underlying clusters are making sure that the right number of pods are running, etc. So, it's not such a catastrophe to have your entire federation control plane go down, other than the fact that you lose API access to it. But your application carries on running largely unaffected. And the same goes for individual clusters, by the way. If you lose an individual cluster in the federation, the services generally carry on running. Yes?
If I have 2 clusters and I have a federation control plane, and I'm upgrading one to a new version of Kubernetes, is it a sensible thing to have them, like, can the cluster continue, can the control plane continue to deploy things onto those if it's occurring, or is that problematic?
If you have clusters on different versions of the Kubernetes control plane software.
Well, the clusters themselves,
Yes.
one's like 1.4, one's 1.2.
Yes.
I'm like upgrading.
Yeah, that's absolutely fine. What will happen is if you have an outage, depending on how you've deployed your Kubernetes clusters, you could do that upgrade in a way in which your API remained available, in which case the Federation wouldn't care. It would keep communicating. We have API backwards compatibility, so everything should work fine. If you have an upgrade scenario where the API server goes down for some period of time, the Federation will see that, will mark it as, you noticed when we listed the clusters earlier on, you had ready, so your cluster will become unready for some period of time. And then depending on how your deployments, et cetera, are set up, it could actually move replicas to a different cluster for you. And that's all optional. So you can either configure it in such a way that the cluster will remain as it is, or that the Federation control plane will redeploy the replicas into other clusters for you.
Is there no circumstance where objects in two different versions of Kubernetes, the definition of it has changed, where like, because the concurrent presentation, they mentioned building a tool that's supposed to manage objects which will change across versions. Is that not occurring?
Yeah, it's a little bit outside of the scope here, and we've run out of time, but happy to talk about it afterwards. We do have, full backwards compatibility of APIs. So a client talking to a cluster can assume that it is talking to a version 1.4 cluster, even if it is talking to a 1.5 cluster. Yeah.